like slowly and measured as possible. And once again, if you do have any problems understanding me or something that I've said, or if you're not understanding exactly a certain example that I've did, please contact me, send me an email, or get to your class representative or a teaching assistant, and they can also contact me. Right, so I'm sharing my screen, and as always, most of the time I remember to tell people I share my screen, but if I sit here talking about things on my screen and you only see me, just let me know. Drop a message in the chat or send me a quick email, and then I'll remember and try not to do it. Because sometimes I do that. It happens. Right, so I'm sharing my screen. And on that screen, you should be seeing a Excel sheet of this specific class. Okay, so we had our class yesterday, the Wednesday class, and then on Thursday, which is today, we have this double period, but luckily it is broken up, I guess, with your evening break or whatever. So hopefully how this will work is that we will have our class now. You can all just leave the session. I'll leave the session open, and then in the afternoon, I guess for you it'll be 7 o'clock in the evening, and for me it'll be 1 o'clock. Then we'll just join again and we'll continue the class from there. So I won't be sending a new link for the class. We'll just be joining this link or this class link. But just if you want, you can just leave the session. I will be leaving the session. But that doesn't mean that you cannot contact me. If in between the sessions, if you have a quick question or comment, just let me know. Okay, so on the right side, just to point attention to that. So this week's classes, we will be mostly doing with the theory and also the introduction. And that's what we're doing now. And this has to do with the PowerPoint presentation. And if we have time later in the class, then I'll start the introduction of the Eagle CAD software, but we'll see how things go. For next week, we have a class on Monday. For you, it's 10:25, and also the same class then on Wednesday, and then the same classes on Thursday. So next week, we will start with circuit simulation. So we'll continue on looking at the Eagle CAD software, the environment of the software, where things are and how to create circuits, and then we'll simulate a couple of circuits. Now we'll simulate normal resistive, capacitive circuits and so on and so forth, but we will also be simulating some analog circuits with transistors and some digital circuits. But we'll speak about it as we go through them. Now the simulation, as we go through them, does have a little bit of drawbacks, but it's a little bit more basic simulation than we get in other softwares, but we will speak about that as we get to it. And then the next week we have the same Monday, Wednesday, and then Thursday classes. Then we'll start with the PCB design in earnest. Then we'll create circuits, take those circuits to a PCB, to the PCB software, and then we'll create the physical circuits with the PCB. And hopefully I'll also be creating a physical circuit during hopefully the Thursday class, get it sent away to be made, and then hopefully in the last week of classes, the same once again, the Monday, Wednesday, and Thursday classes, we'll continue on with the PCB design, and then hopefully I can be able to show you the circuit that I've made. Hopefully it's back from the manufacturer or from the manufacturer. And then that is it. So we have a very, very, very tight schedule. Then after the class, I think you have a short holiday. And then after the holiday, or I'll speak to the teaching assistant, then I'll send you the exam, just so you have a little bit of time off, just to think about it. And then I'll send you the exam, and the exam would consist of a couple of circuits that you would need to simulate and give me the simulation results, and then also a circuit that you would need to design the schematic, which we'll talk about what that is, and also the PCB design file. And then you'll send back to me, I'll mark it, and then hopefully everybody should pass, which you normally do, because you are actually, I found quite smart students and actually really understand what this is. But in any case, so as we go further, and also when we are creating the, I'll show you the EagleCAD, what I recommend you do, and I do this as well, is that you have like a piece of paper or something to take notes with. And then as I show you things that go through, just make a note of it. And then later on, try and reproduce what I have done in the EagleCAD software itself. If you have multiple monitors, then you can quite possibly follow along. I'll try and go through it as slowly as possible so you can also duplicate the work that I am currently doing. That being said, I don't feel it's especially difficult to learn how to use the software. It is a relatively intuitive, easy to use software, but there are a little bit of tricks that you will need to know to be able to understand what is going on. Okay, so that little bit of administration is now done. So as a recap, this week we are still doing the introduction, and hopefully I start introduction into EagleCAD, but we'll see how far we get with the theory. Next week, we'll do simulation of analog and digital circuits. The week after that, we will start with creating a circuit and then transferring that circuit onto a PCB. Oh, excuse me. And then also the week after that, the final week, we'll do a more advanced, difficult elements, more difficult PCB, and then also do so like the preparation for the exam project that I'll need you to finish. And then we're done. 4 weeks. Quick. Okay, so let's jump into it again, and we'll start with the presentation where we left off yesterday. But just as a sort of like a quick recap of that, so we started looking at what PCBs are, what they are made of, and what we can possibly use them for. And then we also talked about the material that PCBs are made of and why we might choose certain materials over other materials. I also deduced a couple of new terms. Well, PCB is probably one. The substrate, which is the physical backing of the PCB board. I'll show you an example of that a little bit later. And then also we spoke about traces or tracts. So traces or a track is the physical connection of a PCB. And hopefully I can show you this. So this is a PCB I made in, oh, this is one of the first ones I made when I was studying. It's really not that great, but it's a good example to show you what a track is. So obviously these are the components on the one side. We'll speak about that in a little bit. What is going on? And then on the other side, no, my camera is not focusing, are the tracks. And these are the physical connections between the elements. So these are the physical connections between the elements. So those little lines, those are the tracks. And we spoke about what material they are made of. Quite commonly, they are more made out of copper, because copper is a very good conductive material. It is relatively cheap, easy to find, easy to manufacture and manipulate. And but the problem with copper and other more conductive materials like silver, for instance, is that they tarnish. So they react to the atmosphere or to gases in the atmosphere, and then their electrical properties change, which, as we spoke about, this is generally a bad thing, because if you design a circuit, especially more advanced or high frequency circuits, or a circuit that carries a very fast acting digital signal, we design it in such a way that It works under certain conditions, but then if the material that the circuit board is made up of deteriorates due to rust or tarnishing, that degrades its ability to carry your signal. And that signal would then be degraded, and also there's a possibility of added noise being entered into the system. So if you think about it like this, if I usually use a term of if you have a water pipe, right? If the pipe is just, there's nothing inside of the pipe, water is just flowing through it, you have a nice steady stream of water flowing through the pipe. But after a couple of years, you might have some sort of chemical buildup within the pipe, and the water then hits that buildup and starts to inject some what we call turbulence. And then that turbulence bounces with all the pipe, and the water that comes out the end is all not nice and smooth, or as we call the laminar flow. It is turbulent and it splashes around over the place. And now think of that in terms of an electric signal. Now our electric signal, when the pipe is smooth, is predictable, which we like a lot. And if there is some sort of buildup inside of the electrical circuit, the same thing happens. The signal gets bounced between the little track, and then that adds in like noise, which degrades the circuit. Meaning that if it's a communication, so like a communication trace between two digital elements, that communication signal might, and information might be lost, which in generally is a relatively bad thing. So to sum up, well, not to sum up, but just to summarize a little bit, is that when we do use copper, usually we coat the copper in some material, which we'll get to protect the copper from the atmosphere. If we do have exposed bits of the copper to the atmosphere, we either coat it or alloy it with a certain material. A popular element is to use gold, because gold does not react to the atmosphere as so like violently, or not as violently, but as severely as what copper or let's say silver reacts to the environment. So these are all things we need to think about. And but more often than not, the circuits that we will be making, or circuits you might be making, are more made by copper. It's usually because it is the cheapest and the easiest to work with. Right, and I think that's sort of like where we left off. And oh, we also spoke about the trace width, how wide the track is, and then we equated that to by how much ampere or current that track could handle. And I spoke about power loss through electric conductors or resistors, because resistors also conduct electricity. They're not that good at it, so they have a resistance. All electric elements will have some sort of power loss. If you inject a current through it, it will have some sort of power loss. And quite often that power loss is in terms of heat. So the numbers, and I'm sharing my screen again for the presentation, where we left off at. There we go. So these trace width, the 0.01 inch, and please remember I'm using inches, can quite comfortably carry 0.3 ampere. So this is the width. It can also be the cross section of the trace width of the track, so how wide it is. And this can quite easily carry 0.3 ampere. So as the trace becomes wider or bigger, it means it can carry more current, and less of that current will be, or less of that power will be lost through heating up. But as we spoke about as well, this also causes a little bit of problems. If you have to create a very small printed circuit board that fits inside of a mobile phone, for instance, but still carries quite high current, then you cannot use a 10 millimeter thick trace, because that will not fit. So there are tricks and tips that you can use to try and limit the amount of power loss. But we'll also speak about that when we go into a little bit more advanced PCB design. But it's something you have to keep in the back of the head. And as with everything with engineering, nothing is perfect. There's always a trade-off. There's always, well, I can make my trace really wide to carry lots of current, but then the trade-off is you use a lot of material, and that is often the most expensive part of the PCB, is the conductive material, and it is also heavier. So sure, I can carry lots of current, it is wide, and its physical size is then bigger, it's more expensive, and so on and so forth. So you will have to be very smart in terms of how you design your PCB. But this also relates into our general electrical engineering knowledge about how current works, how resistance works. If I apply a voltage to a certain resistor, how much current will flow through that branch, but we'll look at all that a little bit later, and then also simulate that as well in a computer program. Because lots of times the circuits we are creating are relatively complex and not as simple, so simple to just work out quickly by hand. So we do tend to use a simulation software to help us out. So yeah, that's usually what we do. We create a circuit. We check how much current is flowing through each of the branches of our circuit, which we'll look at as well. And then we will then designate how thick those traces need to be. But this is all things we will go into when we are creating our PCBs. Right now, we are going to be on the circuit side. Right. So first, as we spoke about, we first draw a schematic of our circuit. So schematic, okay, and hopefully I have shared my screen and you're all seeing the presentation. So a schematic is just the drawing of our circuit diagram. And we can then use this standard drawing to create our circuit and then test and calculate all the currents and voltages, and also might be power running through our circuits. Now, we all should know the standard symbols for electrical components, and it might look something like this. So we have a schematic diagram, which I'm just quickly going to talk through. This is in the middle here, where I have NE555P. This is a 555 timer integrated chip. If I have a chip and, okay, I might show you what this actually looks like. Because I actually have one soldered onto my board. So that circuit where my finger, I hate this. Okay. Let me actually, I know what is wrong. And let's first have my background. Right. So hopefully my background is now not there anymore and we can all see. So this is a circuit I've designed where my finger is pointing. That is a 555 timer. It's an integrated circuit that I have placed upon my board that performs some sort of function. I can't remember what this one was for. But if I have an integrated circuit like this, as you can see, it has pins on either side. Let me just share the screen again. And the symbol that we quite often use for is this symbol here. We have a square, and on the one side, 1, 2, 3, 4, and usually with these, you would have some sort of dot or indication where your first pin is. Here we have a capacitor, C6. Now, another thing that you might notice is that all of these components are numbered. R7, there's just resistor number 8, resistor number 7, and then most of them, actually all of them, has got some sort of value. This is 1K, and 1K equals 1000 ohm. If it was 1M, it will be 1 million ohm. So this is the standard symbol for a resistor. But as always, it's not that simple. We'll go through when we deal with when we go through the introduction to EagleCAD. Some countries have their own symbols. So that symbol, which I just showed you for a resistor, is the I think the American symbol for a resistor. But a resistor can also just be a simple square, which we will look at. But they all will have ohm values or start with the number R. R for resistor. It doesn't really matter what format you use. If you use the American type of the symbol, or I think it's a British symbol, they all mean exactly the same thing. This is a transistor, Q5. So this is a symbol for a transistor, and I think this is a PNP transistor. Here I have a capacitor. Number C8 is a capacitor, and it is 10 UF is microfarad. It's also some units we'll speak about later, but usually capacitors would have micro, nano, pico, and sometimes 1 whole farad, but that is not really that common in circuits. On just the diagram as well, so this is a capacitor, and this is a non-polar capacitor, meaning you don't care which way you connect the capacitor, it works in any connection. But up here, number C7, the capacitor looks slightly different with a line and a bowed line or an angular line there with a positive on the one side. And that is a what we call a polarized capacitor. And those are quite often the, if I have an example, no, I don't have at hand. An electrolytic capacitor is a very good example of a polarized capacitor, which means that you have to connect it the right way. The one pin should always be connected to the positive side and the other pin connected to the negative side. Because if you connect them the wrong way around, sorry, the capacitor will explode. Explosion is a little bit of a scary term, but it will most often just have a small pop sound and the capacitor will cease to function. So when we are working with polarized components, the schematic will show you or indicate which way you need to connect the capacitor or that component. But just be aware, and this is where your knowledge of circuits and diagrams would come in. But to be honest, we will go through all this. You do not need to memorize what all these symbols mean. When we go into Eagle, you will see the symbols, and the symbols will also be described to you in the Eagle software. So this system is basically made up of a 555 timer with some capacitors, some resistors, and a transistor, specifically to connect to perform some sort of function, which I'm not exactly sure. I think it is simply to create a certain periodic signal. And here we have a power delivery chip, not that important. And then a symbol which you might not be so familiar with is this GND. So all of these GNDs, so like the downward facing triangle, is a symbol for ground. Now there are also quite a number of symbols for ground, which we will have a look at in EagleCAD. And also we have VCC, which is usually the supplying power. So a lot with all these circuits, we will obviously go through everything. And when we are creating our own schematic diagrams in Eagle, I will talk through all these as well. But in terms of this, VCC and ground usually is our external power coming in. Now, external power might be a whatever power source. It can be a battery, a solar panel, whatever. It can be some sort of power, but usually we use these symbols on our schematics to indicate what they mean. But as I said, once we go through Eagle and the simulation of circuits, all of this will become more clearer. Right, back to the presentation. And this is just an example of a simple circuit that we might use to create. And now once we have the circuit, we can simulate the circuit and calculate how much current is running through each of these branches. Now, what I call branches are these little connections. So how much current is running in this branch connecting this capacitor C7, C6, and my 555 timer. And then we can use that information. If we calculate how much current running through this, we can use a table like this to select the correct amount of trace width, how thick our traces needs to be. But we will go through this all in good time. I'm just introducing this. And just for the sake of being through a small overview of basic electric rules. As we should all know, voltage, electric potential difference, and this comes into play if most of our power sources, especially batteries, will be indicated in voltages. Current obviously is ampere, or the electrical charge carriers like electrons, and that is a very important factor to consider how big our tracks need to be. And it also comes in what components we need to choose, because some components can only carry a certain amount of power, which is usually power voltage times ampere, or there are other formulas for it. As a sort of a quick example, these are very small resistors. I'm sure you are all aware of these resistors. These specific small resistors, I think, are a 1/4 watt resistors, meaning that they can handle 0.25 watts running through them. Meaning, if I have a 4-volt battery source, it can only really handle what 0. something ampere. So never do maths during a live presentation. But these 1/4 watt resistors are designed for a very small amount of voltage and current. So during our calculations, it's not only important to do those calculations to designate how thick our tracks need to be in terms of energy dissipation or electrical dissipation or heat dissipation, but it's also important in terms of what components we actually do need, because these are really small, really cheap resistors, but they cannot carry a lot of power. Like a 1/4 watt is not much. But for a lot of applications, they are basically enough. So all of these is really important to consider when you're designing your circuit. And a lot of these, we'll talk about this as well. We have some certain like safety factors in case we have a violent voltage spike or a violent ampere spike, current spike that might damage your circuits. We might build in a factor. Let's say we've calculated that a 1/4 watt resistor should work. But if we have a safety factor of 2, we multiply all of those ratings with the value 2. So then instead of a quarter watt resistor, we might use half watt resistors. And a lot of these printed circuit board designs, for certain industries, you would have set safety factors. Because in any type of circuit, a fault could happen, a fault meaning a short circuit or one of your components not behaving in a way that it should, and that might damage your components. So sometimes we have a rating or a value built in to multiply our maximum watt ratings with a certain value, just to ensure that our circuit can handle some sort of outside interference or outside spikes. Now back to the presentation. We also have inductance, then we have capacitance and also resistance. So this is more to do with like our basic components. On most circuits we are going to be working with would have some resistance, capacitive, and inductive value. I'm not going to explain too much about what inductance and what capacitance is. We will have a look at what they are and how they are and what they are constructed of, because that might be a little bit relevant in printed circuit board design. Because it's like the basic description of what an inductor is, or the basic description of what a capacitor is, we might inadvertently build our own capacitors or build our own inductors in our circuit without even knowing it. But we'll go through a couple of examples of that when we dive more into the component selection side of this. So this is a very simple series circuit. Just to give you an idea of what a circuit that we, a very, very simple circuit, we will probably create this in EagleCAD a little bit later on. Here is our power source. Now it's not designated what type of power source it is. It is just a DC direct current 10 source, and it is connected in series to R1, R2, and R3. Now, I'm pretty sure most of you know what the difference between a series and a parallel circuit is. But just to reiterate, a series circuit is when all of the components are connected on the same branch, I call this, and they share the same current. So here, the current running through all of these elements would be the same, and we can calculate the total resistance by simply adding up all of our series resistance. Where is that? So in the series circuits, we have all the resistance value, and then V equals I times R, which is my favorite equation in the world. Voltage equals current times resistance. Now, let's get that ready. So how do we calculate the voltage over each of our resistors? Well, probably the easiest way would be just to calculate the first calculate the total current flowing the resistor. So we would have all of our resistors added up. Put this into our equation here. Have our total voltage 10 volts there, and divide voltage via resistance, and then we have our total current. And then we can multiply our current with our resistors to calculate that. So this, once we have like the total current and the total voltage, we can then calculate the what the values are for our components and how thick those tracks should be. So let's just do it quickly. I actually did not do this. So we have a total of 250 ohms. 10 divided by 250. and we have a total of 0.5 ampere running through our circuit. So that's very important. So 0.5 ampere running through our circuit. That would indicate our trace width. So the minimum value we need for our trace width. So we remember 0.5, and then we can calculate our component values, but then multiplying the voltage that's across on these resistors. But we're not going to do basic equations like this. We're going to let the software do it for us. This is just an example of this. So if we have 0.5, we go back to our table, and 0.4, so you always look at the next highest value. So 0.02 inches should handle our 0.5 current relatively easily. Now, this table is not something that you need to memorize. Most CAD softwares has this connected inside of them, or have some form of this table or a circuit checking software that would tell you, we recommend that your trace would create this much amps or carry this much power, and then we recommend that your trace should be this thick, for instance. But as with everything nowadays, as with all the technology that seemingly gives you all of the answers all of the time, it is always a good idea to check everything, because we are all training to become engineers, hopefully, or something to that effect. And a lot of the times, or not all the times, when we design these circuits, you will have to check those values. So if something goes wrong, the program acts in some sort of mysterious way and gives you the wrong values. You don't check it, you use those values. Something goes wrong, then you are responsible. And that has happened to me before when I started working. I designed a circuit, simulated it, used the values that it gave me, and didn't think of it. But then, like a week later, when the boards were being made, we tested them, something didn't work. I had to figure out what was wrong, why my circuits didn't work, and it ended up that I made a mistake, and then due to my mistake, the program that I was using just repeated that mistake, and then it ended up that the circuits didn't work. So then I needed to redo all of my work and get all the boards that we manufactured at that specific time remade. So that is why you will always have to understand how all of this works, because all these programs are just as smart as you are. And a lot of the times, if you do not understand what you are doing, the program will also make errors. So yes, EagleCAD does check your work and does do some simulations and calculations on the circuit, but it is not 100% foolproof. You will still need to understand what is going on in the circuit, and you will still need to do some calculations, some checking to make sure that it works. Right. Sharing back again. Right. And now we come back, I have shared my screen. Hopefully you're just seeing my screen and not me. We come into parallel circuits. So parallel circuits happens when the current or the current coming in gets divided between sources. Now, this makes it a little bit more interesting to calculate what is going on. But we can still use our same electrical knowledge to calculate the total resistance, calculate all of the current flowing through each of these branches. So this will be a branch, this will be a branch, and this will be a branch. But looking at this specific circuit, I did make a mistake, but I decided to keep this mistake as it is. And my mistake is that after my R2 resistor, this 200 ohm resistor we have on this side, I connected a branch basically in parallel with this R5 resistor. But what does this do? Well, basically, I am shorting out my R5 resistor. And I'm also now going to be talking or introducing the terms of a short. You might have heard it. Hopefully, you know what that is. It is just when I create an easier path for my current to flow instead of the path that I initially wanted to flow in. So it's very easy to short a battery. If my battery is connected to my circuit and I just connect the positive and negative sides to the battery, that creates a short. And then quite often my battery will catastrophically discharge and be damaged. So in my case that I've created here, I have created a short, meaning that all of my current will flow through this branch that has not got the resistor connected on it. So the current, as you might know, divides according to the resistance of each branches, and this branch has got a very, very extremely low resistance value. So almost all of the current will flow through here, and my R5 resistor will not see anything. Now, once again, this is a mistake that I made and then created inside of my program. So my program doesn't know that this is a mistake. It just creates a circuit, and then I can build the circuit. And only afterwards I will see like, oh, wait, I created a circuit that is not working. So it always comes back to your personal knowledge that you will need to understand how a circuit works. And if you've created a circuit that physically actually won't work. So this circuit is very simple, but it's just an example of how you can accidentally create a default or defective circuit. So this circuit, if it's a more complex circuit with hundreds of components, it's probably not as easy to detect these faults. But whenever you do simulations or calculations on the circuit, you will somehow find out or see that some elements or somewhere in your circuit, the values are too high, and then simply you'll have to find it by yourself. Because quite often the program will not be able to show you where your problem is. I'm sharing my screen back again. So we can use all of our electrical knowledge to analyze the circuit, and then also use our software, EagleCAD, for instance, to help us with the calculations. But I am stressing this point, and I have to stress it all of the time, is that you will have to understand how your circuit makes, what your circuit do, what it does, what it doesn't do. And it quite often it ends up on you because you might be making a mistake, but the program is not smart enough to catch your mistake. So you will have to be creating or understand what you are doing during the circuit creation. Right. It's now 45 minutes past. Let's have a quick 5-minute break. Do what you need to do. I'm going to have a drink of water, and then I'll see you in 5 minutes.